Hey, everybody. So in the last video, we were examining this idea of instantaneous rate of change and this tangent line problem. I'll revisit it in a second. But our solution to this problem was something I said we call the derivative. And to come up with this solution, to define this derivative, we first need this little piece of machinery, mathematical machinery that we call the limit, or the limit of a function. So we want to start examining limits in a little more detail. And just as an aside, I guess, we won't quite go into the full detail of the most technical mathematical definition of a limit. In this course, we will mostly think of them intuitively and build some rules to help us work with them. But it is a much larger topic with a lot more structure to explore down the road. Okay, so let's go back to this question of the tangent line. And last time we looked at the function f of x, and the idea was we wanted to come up with a notion of the tangent line at a point, right? And this is where the trouble was, because when you talk about slope, you're talking about change in y over change in x. But if you're only looking at a single point, there is no change. And the method we came up with is what I have illustrated in this graph here, is that we can approximate the notion of this tangent line with these secant lines, right? So here's the point 1, 1, where we want to create this tangent line. So if we look at secant lines, using the point 1, 1 and nearby points, right? So here I'm using a variety of points getting closer and closer. We see that they appear to be approaching something, right? There's like kind of, if you just sort of imagine, right? Here's where the computer can't compute anymore. We can do the same thing from the other side. There's a line that we can all imagine, and I can actually throw on the screen here, that seems to be what was happening to those approximating lines as we got closer to that point. So let's look at this idea in a little more detail, right? So the way that we constructed this is we let h be a small number, right? So this is this is some number that's smallish, right? What that means, you can see we're gonna think about it getting increasingly close to 0. What's important is it's not equal to 0. In fact, the absolute value of h is always going to be greater than 0. So I don't care if it's negative or positive. It can be on either side of of 0, but it's never actually going to be 0. And so to create these secant lines, right? We use 2 points: the point 1, 1. And the point 1 plus h, 1 plus h squared, right? Because so h is a little number. If we move from 1 a little bit, that's what we're looking at in this graph, right? So that little bit is changing. I'm making it smaller and smaller here. So here's the 2 points that we're going to use to create the slope. And the slope of these approximating lines will have the change in y. So I'm looking at the 2 y coordinates. Here's the second one, here's the first one, over the change in x, 1 plus h minus 1, right? So there's our 2 x coordinates. So then let's do a little manipulation here. So 1 plus h squared gives me h squared plus 2h plus 1 minus 1. In the denominator, we have 1 plus h minus 1, which just becomes h. The ones up here cancel. So we end up with h squared plus 2h over h. So let's look at this slope for different values of h. Right? So we'll take a value and we'll make those values of h smaller and smaller, closer to 0, but never equal to 0. So let's make ourselves a little table. Let's call this, I'm gonna make this slope a function, right? Notice depending on what h we choose, we'll get different values for the slope. So here's h, here's m of h. So let's say we started with 1. If you put 1 into this equation, you'll end up with 3. If you put, let's say a half, 0.5, you'll end up with 2.5. You can do the calculations. If you put 0.1, you end up with 2.1. Let's do a few more. Let's do some negative ones. I'm going to throw 0 in here, but it doesn't exist here, right? This function does not exist because it's got a 0 in the denominator. And even though it would have a 0 in the numerator at the same time, 0 over 0 is not defined. And let's just put in some of our negative values. 0.5, we get 1 point, sorry, let me do 0.1 first. 0.1, we'll get 1.9. If we do negative 0.5, we get 1.5. And if we get negative 1, we end up with 1. Okay. Now, notice what happens if we look at this from both sides. If we look at it starting from h getting closer to 0 from above, going down towards 0, excuse me, and h going up towards 0 on the negative side, in both directions, it appears that the values of the slope get closer to 2, right? And I could put in more zeros here, 0.000001, 0.00000, right? I can put all these ones and I'll just get increasingly closer to 2. And you can check this by doing the computations. So what's going on here? Well, let's think of a similar but not quite the same function, right? Notice if I take h squared plus 2h over h, I can factor out an h on top, cancel those factors, and I get a nearly equivalent expression. It's not the same expression, right? The difference is the thing on the left is not defined when h is equal to 0. The thing on the right is, right? So this equal sign is actually not true here because I used the move of dividing out a variable in the denominator that could have been 0. And so I'm ending up with something that's not correct. So these are not technically equal when h is 0. So if we look at the same chart, except instead of the function m, I use the expression h plus 2, which this will spit out all the same values as our original expression, except at one place. It's defined here at 0, while the first expression wasn't. Right, so we see a very similar chart, except for this one place where the thing on the left was not defined, but this new expression is defined there. And so this is giving us a little preview of one of the ways in which we'll manipulate these things called limits. The big idea here is that this thing on the left, m of h, does exactly what h plus 2 does, right? This h squared plus 2h over h. As you get closer and closer to h equals 0, they both get closer and closer to 2. And there's this small difference that this one can actually get there, this one can't. But what we'll find about limits is limits don't actually care what happens at the value, they just care near. And so because these are exactly the same thing near h equals 0, not at it, they have the same kind of limit there, right? And this is how I determined that this tangent line, notice this equation here, has a slope of 2, because that's what this slope formula was approaching as I took h to be 0. And that's exactly the place where the computer can't compute it because it has a 0 in the denominator. That green one disappears, but this is the line that it was looking like it was going towards, okay? So this is the big idea of limits. So let me write down a definition, and then it'll probably be more illuminating to just think up through some examples, okay? Because this is not the most technical definition we can give, but the technical definition can be, creates quite a bit more work to have to understand. And at this point, we just need to be able to work with limits and start building our intuition around them. All right, so here's our definition of a limit. Let f of x be a function defined on an open interval containing the real number a, except possibly at a. Okay, so we're starting with a function, right, defined on some open interval. So if we have a number line, there's this real number a, it just means on some interval around a, the function's defined in that interval, except possibly at a. It may or may not be defined at a. All right, except possibly at a. And we're gonna let L be a real number. This can have any value. We say the limit as x approaches a or goes to a of f of x is L. And we write, so here's our symbol for this notion of the limit. We write lim, we have this, our x, here's our x approaching a or goes to a. So the limit as x goes to a of f of x equals L. So we say this and write this to mean we can make the values of f arbitrarily close to L by taking x close to a on either side, but not equal to a. Okay. All right. So this definition is a handful, but let's go through it a little bit. We're going to do a few examples here. Let's first look at the one we just did. We had this function m of h. All right. So let's just think about how we wrote it here. What I was demonstrating in this with these tables is that the limit as h goes to 0 of m of h is equal to 2. Okay, so this is what I was demonstrating in this little exercise, right? So using our notion. What we mean by that is I'm claiming that this function h squared plus 2h over h, that I can get it as close as you want, as anybody asks me to the value 2. All I have to tell you is how small h has to be, how close to 0 h has to be, right? So for instance, if you want me to be less than half a unit from 2, if you want m of h to be less than half a unit from 2, if you want m of h to be between 2.5 and 1.5, right? That's less than half a unit from 2, either side. Then I simply have to insist that h be between 0.5 and negative 0.5, right? I think this is clear enough from these tables. Notice this is an easy way to compute it, is looking at this equivalent or nearly equivalent function, h plus 2, those are the same functions except at 0, right? They're exactly the same except at one place. But notice the definition of limits doesn't care about what happens at the place we're taking the limit, in this case at 0. It doesn't care about what happens there. And so it's easy enough to see that if I want to make m of h between 2.5 and 1.5, as long as I pin h between 0.5 and negative 0.5, like 0.1 and negative 0.1, right? Those are closer to 2 than half a unit. And if you come back and give me a smaller interval, like make it less than a billionth away from 2, make m of h less than a billionth away from 2, I'll just make h less than a billionth away from 0. So on either side, it would be pinned in that way. Okay, that's the idea of a limit. So let's look at this even more closely, maybe graphically. So here is a picture of the function m of h. Okay, so using this program, I had to use x instead of h. So you'll see I have the function x squared plus 2x over x. And it has that hole right there at 0, 2, right? If x is equal to 0, this function is not defined. So the idea of a limit is somebody challenges us, right? So here I have a blue line and a green line. That's the upper and lower limit, bound that somebody's challenging us with. So right now, somebody has said to me, are you sure you can make sure this function is less than 1 unit away from 2? Well, look at this graph. So if I want to make sure that the function's not bigger than 1 unit away from 2, so saying within 1 unit of 2 means it's going to be between 3 on the top and 1 on the bottom. Looking at the graph, as long as I keep the x values to the left of the value 1, the function will be below 3. And if I keep the x values above 1, the function will be greater, above negative 1, the function values will be greater than negative 1. And no matter how small a challenge you give me, right? So now we've got this upper bound, right? The blue line is saying, I want to make sure the function, how close the function is to the value 2, right? So now I've got 5/100ths, right? I'm asking you to make sure the function is less than 5/100ths away from 2. And all we have to do is keep our x values between the vertical green and blue lines here, right? Which are on either side of 0 by 5/100ths, okay? And if I'll lose resolution of the computer here, but I can keep getting smaller and smaller, and all that has to happen is that interval for x gets smaller and smaller, right? There's nothing in the definition that says how big that interval has to be. There just has to be some closeness in x that will ensure the closeness to L that was desired. And there's no, obviously the computer can't go any smaller than this. Well, maybe if I type it in. So we're getting incredibly small now. If we zoom in, we'll still see it, right? I can keep adding zeros and the computer will run out of resolution before the mathematics will. So there's no limit, I guess. I mean, there is a limit. I mean, it's a limit to me in 2 different ways. There's no end to how close I can get this and keep it close. Right? Let's look at another function in the same way. So zoom back out. Here's a cubic function. Okay, so this is the function. I think it's just there we go. G of x. Let's go black. G of x is equal to x cubed minus 1. Right? And I want to look at the limit as x goes to 2 of g of x. My claim is that this limit is 7. Okay, so what does it mean to say that? It means that I'm claiming that no matter how close you want my function to be to the value 7, I can get there by giving you a bound on x so that all the values of the function between these two values will be closer to 7 than whatever value you challenged me with, right? Except possibly at x, at 2. In this case, it actually doesn't matter. In the previous case, it did. But we still don't care about what happens exactly at 2, just nearby. So here's our little challenging idea again. So here's somebody says to me, okay, I'm not sure if I believe you. Can you make sure that the values of the function g are less than 1 unit away from 7? So here we're looking between 8 and 6, right? You can see on the scale at the side. Well, I can insist if I look at where these bars, these limits, right, these bounds, I want to be less. Let's look at 8, for instance. Looking at the graph, if I go straight down, we'll hit the x-axis at a little bit above 2 in the case of the function value 8. Let me just write this in. Right, so this is the point. I'm just going to call it 2 plus. It's a little bigger than 2, and it comes out at 8, right? So if you look at this picture, what it's showing you is that below the x value, a little bigger than 2, whatever that number is, my values for the function are always less than 8. And that's one of the limits I wanted, one of the bounds I wanted to have, the function being less than 8. So if I keep x less than this little bit bigger than 2, the function itself will be a little bit smaller than 8. And where's that button? There we go. Same thing on the bottom. We've got a bound at 6. We want to be above 6, closer to the output 7 than 1 unit means above 6. And so we can just look at where this point, oops, wrong one. That's the one. Oh, wait, that's wrong. So, oh, my line's not quite matching. Oh, this is, so there's you can actually see, all right, let's explain this better. If you look, what's happening here, this value at 6 hits the graph right here. And we could make our x values down to whatever this number is. It turns out that the space between x equals 2 and this x value are bigger than the space on this side. And so I pulled them in to make them symmetric. That's usually how we think about these things. So that's why, but it still satisfies the definition. I'm even closer than I need to be on this side because I'm making it match each side. And so we end up with this, let me clear all these drawings. It's the same idea, but I'm just making the bounds symmetric, right? In the linear case that we did first, the function didn't have this problem. It was exactly the same on each side. It doesn't quite work that way when we don't have a linear function. And so we end up with, oops, wrong one, just pulling the bound even closer. In either case, the point is that as the challenge gets tighter, I can still ensure the values of the function popping out are between these two bounds by putting x between what is now a pretty narrow interval, okay? So this is the idea of a limit, right? Right now we're just looking at it graphically. You can see no matter how much I pinch this in, there's some interval so that the x values ensure that the y values coming out, the values of g, are between those two vertical lines, right? And we can always do that no matter how small it gets, okay? This is complicated. It is okay if this doesn't totally make sense. Let me just pause for a moment to give you where we're going next. What our real goal right now is to get a little bit of the idea of the limit, let that start rolling around in our heads, and then we'll develop rules to deal with them, and we'll start manipulating them. And the more we work with them, the more they should start to make sense. They are undeniably difficult to comprehend in the beginning. And it's fine if they're feeling a bit loose for a while. Let's look at some examples that don't work, because it turns out we can't always do this, right? And it might help understand what these limits are if we look at examples that don't work. So here's the function, the absolute value of x minus 3 over x minus 3. And here's what the graph of this looks like. Notice, for instance, that it's not defined at 0. So I called this p of x minus 3 absolute value over x minus 3. Notice it's not defined at 3. Sorry, I think I said 0. It's not defined at 3 because we get a 0 in the denominator. Notice what happens everywhere else, though. Any number we put in, we get the same number in the numerator as the denominator, except for one thing. They may or may not have the same sign, right? So if x minus 3 is positive, right? If x minus 3 is positive, then they're both positive numbers, because x minus 3 is positive and the absolute value of a positive number is positive, and they're the same number, and so you get 1. And so if we're above 3, right, when x minus 3 is positive, as long as x is greater than 3, then we simply are dividing the same number by itself and getting 1. And so this function is just 1 to the right of 3. On the other hand, if x minus 3 is negative, if x is below 3, then the numerator is positive, the denominator is negative, we get a negative 1. So our function looks like negative 1 below 3. So we get this jump at x equals 3, right? And it's not defined there, so they're both open circles. Okay. So now, what if somebody makes that challenge? What is the limit at this place, at x equals 3? Can we take the limit as x goes to 3 of this function? Right. Well, what might we take as the limit? If, for instance, we decide that the limit is 1, right, as the function appears to be 1 on the right, there's no way we can keep the function values close to 1, because as soon as we get below 1, we jump all the way down to negative 1, right? So this is a bit confusing. If I claim, for instance, that the limit is 1, notice that I cannot, right? Remember, we need to be able to keep the values of the function as close as we want. So any challenge, if anybody challenges us, we should always be able to succeed. And right now, let's say someone challenges us and says, I want the values of this function to be less than 2/10 away from the value 1. That's easy on the right, right? It's easy above 3 because the values are only 1. And so every input gives us the output 1. But on the other hand, on the other side, and we need this open interval around the value 3. So we have to look on both sides. And the values are always going to be further away than 2/10 because they're all the way down at negative 1. And so we can't keep the function between these vertical bars. There's just no way to do it, right? Whatever we want to try to do this, it won't work, okay? And so we just end up with this situation where there's nothing we can do to create a limit. If we tried to make the limit negative 1, we'd have the same problem in the opposite direction. You might think maybe we take the limit in the middle of these two and say the limit is 0, but we have the same problem. We can't keep the function values close to 0 near the value 3. They're always at least a unit away, and we have to be able to succeed given any bound, any distance, any value of closeness to the value, to the limit. And so this limit does not exist. Okay, let's do a couple other. I'm going to skip one thing, just make a new video of that. But let's finish on one note. Let's do a little more graphical notions around limits and look at the 3 following graphs. And these are things we've seen already in this video, or at least some of them are. So one thing that can happen actually, we don't need to make it, let's make it less linear. It doesn't have to be linear. So here's a function, f of x, some curve. And if we were, let's say this point here is the point 3, 1 maybe. This is the first kind of limit. And the one when we looked at it was a limit where there's a hole in a function here. And the limit as x goes to 3 of f of x, in this case, we're only talking intuitively. We're looking at pictures, but we're just see from this picture that the function gets closer and closer to what's going on in that circle. And it doesn't matter what happens in that circle. If I alter my function so that it actually doesn't have a hole here, the limit remains the same. Or maybe I redefine the function to be something like some other value, like 311, right? It doesn't change the limit because the limit doesn't care what happens at that point. It cares what happens near it. And if you look at the picture, the value of the functions are getting closer and closer to 1 as x gets closer and closer to 3. So this is one kind of limit that we will see. We also see piecewise functions. So we'll just do this graphically. Say I have a function, right, defined in pieces. This one looks like it has two linear sections and a maybe parabolic section. And let's make this 2, 1, and this was 2, 2. So here's a piecewise function. Let's give it a little structure. So this is the function negative x minus 3 if x is less than negative 1. Negative x minus 1 squared plus 2 if x is between negative 1 and 2. And then 3x minus 4 if x is greater than or equal to 2. Okay, so there's a picture of our function. So let's just think about the picture here. Limit, for instance, as x goes to negative 1 of g of x. We're asking what value does this function look like it's going to as x gets closer to negative 1. So here's where x equals negative 1. And notice if we approach, if we make our values of x get closer and closer to negative 1, the graph gets closer and closer to this point, negative 1, negative 2, which tells me that the limit here is negative 2. I can get as close as I want to that point, that value, that output value for g, as long as I make x really close to negative 1, right, on either side. On the other hand, if I try to take the limit as x approaches 2, I can't do this because the value the function has here, but from the other side, as we approach 2 over here, our function is going to 2 different values depending on which side we approach it. And so it's like the one we still have up in this graph. However we try to come up with the limit, one side of the graph is always going to be very far away in terms of, when we're talking about very tiny numbers, right? If the challenge is to make it closer than 1/10 to whatever our limit is, one of them is going to have to be at least half a unit away, right? Possibly both of them, depending on how we try to define this limit. And so this place, the limit does not exist. And then let's do one more point here. Let's see, this is what was that? This will be the point 1, 2, the vertex. This is just some arbitrary point on the graph. Nothing special is happening there. There's no whole. The limit as x goes to 1 of g of x, well, all the function values are getting closer and closer to 2, right? As I approach x equals 1, I'm coming this way and this way. The values, the outputs are approaching 2, and this limit is going to be equal to positive soon. Okay, so this is starting, I hope, to help us get a little picture of how these limits work. I want to mention one other thing before we finish this video. Another kind of limit that we'll discuss in a separate video is what happens when you have asymptotes, right? So we might have a function that looks something like this. Right. So I think in this case, this was the function k of x is equal to 1 over x plus 1, x minus 1, x minus 2 squared. So here we have an asymptote at x equals 2 and x equals -1, places where the function is not defined. But remember, we don't care if the function is defined or not there, right? In this first example, for instance, before I changed it, this function is not defined at x equals 3, but we can still have a limit there. But here it's not defined, but the function's doing something very interesting, right? In this picture, it's going off to negative or positive infinity, depending on which of these asymptotes we're talking about. So what happens to the function as you approach these asymptotes is another question we're going to explore a little bit more deeply that has to do with limits, okay? So the last thing I'll say is, even in the cases where the limits don't exist, which includes these cases with asymptotes, these limits don't exist because there's no number we can say they're going close to. And this case where there's a jump, the limit doesn't exist, but they are still interesting behaviors. And ultimately, we're using limits to describe the behaviors of functions. We are still going to be able to talk about these using limits. And we'll talk about that in one of the next videos, that while we can't define the limits here in terms of a number, we can use the idea of a limit to still tell us something about those functions. And we'll do more on that in the next one. All right, that's it for this one. Thanks, everybody.